Good morning, everybody. Welcome to Tuesday morning session. I'm Xizong Chen from Peking University. It is my honor to chair the Quantum Optics and Cavity QED session. The first speaker is Mikhail Lukin from Harvard University. His talk is on exploring frontiers of quantum optics with strong coupled atoms and atom-like system. Please, let's welcome.
So I would like to start out by joining others and thanking organizers for invitation. This is my first time in Korea, even though I have many Korean friends. And actually, it's really a fascinating place here with a lot of exciting physics going on. So I will talk today about quantum optics with strongly coupled atoms and atom-like systems. And of course, the topic of exploring strongly coupled atom and photons is actually a long-standing goal of AMO physics. So it's of fundamental importance for things like ultimate control of light quanta. But there are many potential applications also which has been explored over several decades. So these include, for example, ideas of quantum networks. Some of these ideas have been mentioned yesterday already, but also the kind of ideas of quantum nonlinear optics is, for example, exemplified by this single photon switch or transistor. So this is basically a switch where one photon can flip the switch on and off, and the device like this could, of course, be used to generate some very interesting non-classical states of light. These techniques can also be used for information processing, both classical and quantum. And while all of these things have been known for many decades, it is also known that to realize strong and controlled interaction at the level of single atoms and single photons is actually very challenging. So specifically, photons generically interact very weakly with single atoms and also with each other. And photons can also be very easily lost, can be scattered in the modes that you cannot control. And that was a motivation to start exploring some exotic systems to basically coax, to force the atoms and photons into talking to each other very strongly. And this has been, of course, a subject of pioneering work on cavity QED with pioneering experiments in Dan Kleppner's group, and Serge Haroche's group, Herbert Walter's group at MPQ, then later in the optical domain also at MPQ at Caltech. And this topic has been the subject of many ICAPs for over 2 decades. Now, over the last decade or so, something remarkable has happened. So these ideas have been actually transferred from just the field of AMO physics to many other disciplines of physical science. And by now, there is a broad effort across several subfields in exploring interfaces for atoms, ions, superconducting semiconductor systems in the domains ranging from optical to microwave, even all the way to mechanical. And even more remarkably, over the past few years, we have seen some remarkable progress in terms of realizing a lot of these ideas and kind of making them robust. So in particular, strongly interacting photons, the systems where individual photons talk to each other, have been now realized in many different platforms in both optical and microwave domain. Researchers have succeeded in coupling remote matter qubits mediated by photons. And also there is now an intensive work on scaling up quantum information systems using these techniques. So in the session today, and also in, I would say, 2 sessions tomorrow, we'll hear about how these ideas are being applied to very different physical systems. And in what follows, I'll just give you 3 examples from our recent work. Those range from the use of ultra-cold atoms, strongly interacting ultra-cold atoms excited into Rydberg states to create the quantum nonlinear optical medium, the medium where single photons interact, to the situation involving quantum optics and cavity QED with solid-state atom-like emitters. These are basically impurities in a solid state which behave in nonlinear elements, and I'll talk also about how we can use it to create this, systems which are nonlinear at a single photon level, but also I will start talking already how we can scale up these systems, how we can use these systems to create entanglement between matter wave qubits. And I will come back to the ultra-cold atoms at the end of my talk, and will talk to you, describe to you a new approach to scale up neutral atom quantum systems. So the idea of quantum nonlinear optics enabled by strongly interacting atoms is very simple. So basically, what we would like to do is we would like to exploit strong coupling between single photons and an atomic ensemble using, for example, slow light techniques with the excitation of atoms into Rydberg states. And once the atoms are in the Rydberg states, they start interacting very strongly to each other, enabling strong atom-atom interactions. And then these strong atom-atom interactions eventually are mirrored in strong photon-photon interactions. 2 basic concepts underline this work. One of them is the idea of dipole blockade. So if you take a small atomic ensemble and excite it into Rydberg states, so what can happen is that the interaction between Rydberg atom can block multiple excitations, effectively making this entire ensemble behaving like a 2-level system. So this phenomena is known under the name of dipole or Rydberg blockade and has been explored over the last decade in various experiments ranging from quantum information science to many body physics, and recently in the case of quantum nonlinear optics. So in order to strongly couple photons to such blockaded ensembles, we'll make use of the phenomena of electromagnetically induced transparency. Just to remind you what happens in electromagnetically induced transparency, if you have a weak light pulse, can be a single photon or weak laser pulse, resonantly propagating inside the medium, we can actually control this propagation by essentially stimulating and excited atoms into the so-called dark state. And in such a case, the medium becomes transparent, but the light is propagating very slowly through such a medium. The slow light propagation can be understood in terms of the so-called dark state polaritons. So basically, this photonic wave propagating in the ensemble drags along the wave of the excited atoms here. And basically, by changing the control field intensity or Rabi frequency, one can actually manipulate this coupled excitation of light and matter. In particular, this excitation can be slowed down dramatically or even stopped, in which case it's converted completely into the atomic excitation. And then by applying the control field again, it can be restarted and can propagate further. So basically, if we arrange the situation such that the final state of the EIT system is a Rydberg state, what can happen is that basically the interaction between the Rydberg atoms can map into the interaction between this dark state polariton, and it can result in strong photon-photon interaction. So that's a basic idea behind the kind of enhancing nonlinear optical response of the atom. And has been some very nice work in this area by many groups, starting from pioneering work by Charles Adams' group in Durham, and also by Alex Kuzmich group at the time in Georgia Tech. So about 6 years ago, in collaboration with my friend and a CUA colleague, Vladan Vuletic at MIT, we started building an experiment to probe quantum aspects of this nonlinear interaction. And this experiment is conceptually very simple. So here is the cloud of cold atoms is just loaded in a dipole, optical dipole trap. And the critical things which we would like to achieve is we would like to achieve sufficiently high density that the optical depth of this cloud is sufficiently large. And in addition, what we do is then we use a control field which drives the excited atom into a Rydberg state. And by tuning the frequency, we can choose basically the principal quantum number ranging from something like 50 to about 100. And that allows us to control the Rydberg blockade radius. So in fact, in the experiments, we typically choose Rydberg blockade radius between 3 and something like 20 micrometers. And that results in optical depth of this blockaded region, another important figure of merit of between 1 and 20. So we have now several generations of students and postdocs who worked on these experiments. And about 4 years ago, actually at the ICAP in Paris, I presented some very first results where we've observed basically a photon blockade. So if you send resonant light in this medium, what happens is that the two photons can just not propagate in this medium simultaneously, and that results in anti-bunching of the laser light, which is passed through the medium like this, once you excite the atoms into sufficiently high Rydberg state with sufficiently high principal quantum number. Since then, we have extended this phenomena, these experiments in a number of ways, and in particular, by going away from resonance, we were able to observe coherent interactions. In this case, the photons become attractive. We were able to see, for example, bound states of photons, formed through this kind of, strong photon-photon attraction. The key goal of this work is now to make these interactions deterministic, robust, and coherent, and such that basically they are very strong. So this is required, for example, for applications in quantum information processing, but it's also required for studying many-body physics with photons. So I'll just tell you a little bit about one of our most recent experiments in this field. And basically, here what we do is we study controlled collisions between these EIT polaritons. So this is done by using the so-called photon transistor type setting. So the idea is that you first start with the photon, say a single photon or a weak laser pulse, which you use as a gate. So basically, you let it inside the medium, and then it slows down, and then eventually you turn off the control field, and this pulse is basically stopped inside this medium. So once this pulse is stopped, the single excitation now is transferred to this Rydberg state. And what we could do, we can hide or shelve this excitation coherently by applying a microwave pulse and driving the transition from one Rydberg state to another. So that was a gate photon. So then subsequently we send a probe photon. And what this probe photon does, it now can propagate inside the medium, and it can interact with this stored gate excitation. So subsequently, we can also retrieve this gate excitation by applying another microwave pulse and just letting this photon propagate out. So we're basically now interested in looking at correlations between this gate and the probe photons. And one important aspect which we can employ here is that we can actually engineer now the interactions between polaritons by choosing the state where this gate photon is stored. So in particular, we will be exciting with original polariton, 100S state, but we will be storing this gate polariton in 99p state. So the reason why this is important is because in this kind of S to P transition, there is a direct dipole-dipole interaction, which actually scales as 1 over r cubed. It is actually much stronger and much longer range than the typical 1 over R to the 6 interaction. So in the case like this, you can actually create a situation with the blockade radius of about 20 microns, which have an optical depth exceeding 10. So basically, in this blockaded region, you would expect that the probe transmission will be attenuated by substantial factor. Yet, when we start doing this experiment, we have observed something quite different. So basically, in these experiments, what we do, we look at basically a probe transmission conditioned on the retrieved gate photon. So basically conditioned that we retrieve and detect one gate photon, we look how much probe is transmitted. And what we do is we increase the optical density. And so initially what you see is indeed as we expect, this conditional transmission goes down, but then the trend changes and actually the transition starts to increase. So what is going on here? So note that this is actually very special for 99p gate state. If we start with 99s gate state, it's a different state which we can store. The transmission is not very good. So it turns out the origin for that is a coherent excitation hopping. So basically the nature of this interaction between 99s, 99p and 100s state is a hybridization of this kind of s and p orbitals. And basically what this really means is that if we come in this state 100s and 99p, what will happen is that the excitation will start hopping back and forth between these two states. And this excitation hopping Rydberg excitation hopping result in hopping of the probe polariton and a stored spin wave. So basically it's described by this kind of very simple equation where we have two excitation wave function, which is described, which has some propagation term, and then has this kind of exchange interaction, which basically changes the coordinates of two excitations. So what this really means is that if we started with first propagating polariton, so basically as it approaches a stored spin wave, rather than getting absorbed, it actually jumps and kind of moves forward. So is this interaction coherent? Is it useful? So to answer this question, what we can do is we can look at coherence and a phase shift in this polariton exchange. And the way how to look at it best is to look at two modes. One mode is initially stored, it does not move, and another one is moving. And when they approach each other, they undergo this kind of exchange process. But in this process of this exchange, they are, so to say, rotating around each other. So it's like kind of like a pi pulse, if you want, for a two-level system. And in the process of that, they actually pick up the phase. So this phase turns out to be equal to the pi over 2. So it's exactly what happens with the resonant pi pulse. And actually, this phase turns out to be robust, very robust. So this robustness, it turns out, is actually fundamentally related to the symmetries associated with this kind of propagation equation. And actually, the symmetries which protect the robustness of this phase turn out to be very similar to the symmetries which protect the Majorana fermions in condensed matter systems. So to probe this kind of phase, what we simply do is we basically inject we mix this transmitted light with a local oscillator, which is detuned by a few megahertz. And basically there we can directly look at the conditional phases in the transmitted pulses. And if we look at this as a function of optical depth, we immediately observe that as transmission starts to increase, this phase approaches this kind of universal value pi over 2. So this hopping produces robust phase shift pi over 2 with actually quite high transmission. And this results really in coherent, robust interactions between polaritons. So we're actually quite excited about this because it really opens up for very intriguing possibilities to make these photon interactions robust and kind of reliable. And in particular, we are now thinking about extending this phenomenon to many body systems where perhaps one could explore some topologically protected quantum optical phenomena, quantum optical effects. So at this point, I'd like to shift gears and talk about a very different experimental systems that instead of cold atoms make use of atom-like impurities in solid states. So in particular, I will be talking about color centers in diamonds. So these are basically impurities which give diamond a color. And over past decade or so, those defects, have emerged as a kind of new, very exciting quantum platform, which is explored now in applications ranging from quantum computers all the way to kind of nanoscale biological sensors. Fundamentally, the reason why we're interested in working with these defects is that we would like to combine the best of all worlds. So you all know that isolated atomic systems are known for their excellent coherence, while typically one can think about solid-state systems as featuring very strong interactions and potential for integration and scalability. So we would like to try to basically put all of these good features together in a single setting, and these atom-like systems, in principle, at least provide such a platform. So one particularly well-known example in this area is the so-called nitrogen vacancy color center in diamond. So it's one of the many stable impurities frozen in diamond, where basically nitrogen replaces a carbon atom in the diamond lattice, and there is a vacancy nearby. So these two form a stable kind of molecular-like color center, which you could say to a first approximation really looks like nature's own trapped ion. The reason for that is that it's a color center. It can be excited and observed optically. So for example, if you look at a reasonably good diamond sample on the microscope, what you can observe these individual dots which look the stars in the sky, maybe not in Seoul here, but somewhere in the countryside. But these single dots are really single individual color center, which are like single atoms. And in addition, the impurities like NV center also has a non-trivial spill property. In particular, NV center is actually a spin triplet. And you can polarize and read out a spin state optically. And most importantly, the spin degree of freedom can be extremely coherent. So in fact, it can have millisecond coherence time even under ambient conditions at room temperature. So for this reason, and last but not least, these kind of color centers can be created in nanoscale structures by basically starting with a pure sample and just bombarding them with, say, nitrogen ion and subsequently annealing this sample. So for this reason, the color center, like NV centers and others, are being now very actively explored as quantum registers, and indeed they have been used to implement small-scale algorithms, quantum error correction. And in fact, just about a year ago, the group in Delft used these NV centers to create an entangled state separated by kilometers and perform the loophole-free Bell test. But there is a challenge in this experiment, and this challenge is that, in the words of actually Chris Monroe, who started kind of one of the pioneers in the research in this area, is that these kind of experiments work well when they work, but they don't work very often. So what this means is that basically this, the challenges in efficiency, basically, for example, in these Delft experiments, it took a long time. Basically, it took a few minutes to get to create one entangled pair, and that means that it took many attempts and all kind of one had to repeat it many times. So basically, the challenge is to design some interface between these color centers with photons, which is both efficient and coherent. So motivated by that, we're actually exploring a new approach to cavity QED. And the idea here is to basically confine photons in the very small mode volume in systems like shown here. So this is one-dimensional photonic crystal, which has a mode volume smaller than the cubic wavelength. So this is basically the electric wire in which we make holes, and basically, the electric wire confines the photons in the transverse direction, but these holes result in reflection, multiple reflections of the light wave, so they create kind of a Bragg structure, which then confine light in the direction of this wire. And basically, if one can succeed in confining light to the mode volume smaller than the cubic wavelength, it, of course, immediately results in very large single photon Rabi frequency. So this will naturally create strong interactions between atoms and photons. And basically, what we only need to do now is we need to somehow place some emitters, such as, for example, cold atoms or atom-like emitters, somewhere in a near field of this device. So not only we need to place them, but we also want to make sure that they are coherent, controllable, and hopefully identical, because eventually we would like to have many of them. So atom-like systems, of course, appear to be very natural for this purpose. And the reason is that, basically, they can exist in the structure itself. So you don't need to worry about, for example, cooling and trapping. All you need to do is just basically direct the emission into the desired modes of this nanostructure. But actually, it turns out that really implementing this is very, very challenging. There are multiple reasons for that. So first of all, most of these emitters are much more like molecules rather than the atoms, in the sense that if you excite it, rather than just decaying back, it actually decays to a lot of these kind of vibrational states. And basically, what this means is that it returns to the ground state by emission of the photon and subsequent emission of the phonon. So what it means is that if you look at NV center fluorescence, even at low temperature, what you typically observe is you observe this narrow coherent line. It's so-called zero phonon line, but then it's a very, very small fraction, about 5% of total emission. The rest is this kind of broad so-called phonon sideband, which, of course, produces light, but it's not useful for quantum optics application. It's completely incoherent. But it's only the beginning of the problem. So even if you zoom in on this, if you just select and zoom in on this zero phonon line, what you often find is that it's actually not very narrow. In fact, it differs from one emitter to another, so that's a problem of inhomogeneous broadening. Moreover, most emitters do not, for most emitters, this zero phonon light is not even stable. So what this means, and this is a particular problem for a nanostructure, what this means is basically, if you scan the laser, what you find is at one scan, you find a narrow line, but it's actually in one place, but then you scan it again, and then the line is in a different position. And so it kind of is wandering around. So basically, each emitter has its own local environment, and moreover, the environment changes with time. So that's a big problem. So I actually spent a number of years trying to basically make NV centers behave like it's shown up here, behave coherently and make it stable. And actually, in the process, we figured out an elegant solution to solve this problem. And one solution is very simple, is to replace nitrogen atom in this impurity by a silicon atom. So actually, silicon atom is a little bit larger than the nitrogen atom, and as a result, it cannot fit in one of these kind of empty carbon lattice sites. As a result, it's actually the so-called interstitial defect. So it lives in between these two kind of empty lattice sites. So it turns out that this simple change in the kind of structure of defect has a profound property. So in particular, this silicon vacancy has much stronger zero phonon line, and what's most important is this zero phonon line isn't sensitive to electric field. Why is that? Well, it turns out the reason for that is quite fundamental. The reason is that this silicon vacancy center has an inversion symmetry. So as a result, it actually has a zero dipole moment in both ground state and the excited state. And this is contrary to V center, which lacks this inversion symmetry and has non-zero dipole moment. So as a result, this silicon vacancy center behaves much more like atom. So in particular, to the leading order, that its transitions are insensitive to electric field. It results in suppression, spectral diffusion, and also has low inhomogeneous broadening. So what this means is that if you take a diamond sample with some of the silicon vacancy centers and just pick two random emitters, if you basically scan across the line, you find that they are practically overlapping. So they actually they are lying on the top of each other. So that's, of course, a very nice starting point for doing optical experiments. But one thing that I would like to mention before we go on with describing those is that, of course, silicon vacancy center has also some spin. It actually is a spin 1/2, and it also has some orbital structure. So it actually turns out that in the ground state, it has a kind of spin orbit split doublet, and basically, all of these transitions can be driven with optical fields. So basically, you can use, for example, lambda systems, dark resonance, to manipulate these coherences here. Okay, so starting with that, what we have done is that we basically fabricated photonic crystal devices out of diamond by basically carving nanostructures out of diamond. So this is one of those devices. So basically in this device we have two portions which are basically waveguides, photonic crystal waveguides, and then another section where we modified a little bit the spacing between the holes and thereby creating photonic crystal cavity. And then right into this area where we fabricated the cavity, we actually implant silicon ions by using focused ion beam. So once we have done this, we can actually probe the transmission through this coupled system of the cavity and silicon vacancies. And what we observe is this kind of broad cavity resonance and this very narrow, very nice transmission dips. And if you zoom one of them, we can actually easily check that these are extremely nonlinear. They are saturated with less than 1 photon per lifetime. And actually from here one can directly extract, for example, a cavity QED parameter. So in this case, the cooperativity was on the order of 1, but the single photon Rabi frequency is actually very, very strong. It's about 2 gigahertz. So that's, of course, a very promising starting platform for doing experiments in quantum nonlinear optics and also for scaling up the systems. And some of those will be discussed in details by Raffin Evans, who has a poster here. But so let me just describe briefly just a flavor of what we can do with a system like this. So the simplest experiment we can do is here is to basically look at transmission through this coupled waveguide, cavity, and the emitter system. And the idea is that if this emitter is coupled very strongly, then what will happen is that if we send very weak, say, single photon pulses, they will not be able to make it past this emitter. So they will be always reflected. But this is a two-level system. So if you send, for example, a pair of photons, one of them can saturate it, and then basically this pair can go through this saturable quantum emitter. So what this really means is that this simple device like this already acts as a kind of single photon sorter. So it actually preferentially transmits pairs and reflects singles. And if you combine this kind of system with a memory, one can also implement this kind of single photon transistor. One can do atom photon gates and things like this. And actually, it can be easily, these experiments can be easily checked by just looking at photon correlations of of basically reflected or scattered light and transmitted light. So for example, in this case, if we excite this system and look at scattering, we observe anti-bunching. But if we look at the photon correlations in transmission, we actually observe bunching. So that really is a signature that these single photons are reflected and photon pairs are transmitted. And we have actually, using the memory, we also have extended these techniques to actually realize, for example, these single photon transistors. But what's particularly exciting about this system is the possibility to scaling up. And actually, to scale up, it's very important that these emitters can be tuned into resonance, that they are made indistinguishable, identical. So as you've seen already in the spectra that I presented, these silicon vacancy centers are very close to resonance, but not quite identical. So, and the reason turns out for that is a strain in these photonic crystal devices which we produce, but actually we can make them identical, and the idea simply is to use a Raman transition. So basically by just changing the control field intensity, we can tune this Raman photons. I think there are 5 minutes and plus questions, right? So, okay, so we can tune them into the resonance, and then what we can do is we can entangle them by simply exciting these two emitters and basically, for example, using some of this probabilistic detection entanglement scheme that was described by Chris. So, for example, if you detect a single photon and you do not know from which emitter this single photon comes, you prepare this so-called super radiant state. So the super radiant state is actually has a twice the emission rate compared to just individual emitters. And actually, once you create the state, you can verify the presence of the state in photon correlation measurement. So specifically, while individual emitters, the two emitters, if they are distinguishable, they would correspond to G2 of 0.5. If you create this bright state, then this G2 observed in this kind of photon correlation states will be a laser light, will be actually equal to 1. And we observed this in the experiments where we basically excite these emitters first individually. In this case, G2 is equal to 0. If we excite distinguishable emitters, we observe this G2, which is close to 0.5. But if we excite indistinguishable emitters, we observe this new interference feature. And from this new interference feature, we can really extract not only the presence of entanglement, but also characterize things like concurrence, conditional fidelity, entanglement rate, etc. So we're also very excited about these new developments, and it really creates some very interesting possibilities for scaling up the systems, for creating networks, and also exploring some exotic photonic systems like walls involving spin-orbit interaction. So in my last 3 minutes, I'd like to switch gears again and return to cold atoms. So in principle, ideas like this, systems like this, can be also realized using cold atom systems. And again, 4 years ago at the ICAP, I talked about the first results where we were able to basically take individual atoms, put them in optical tweezers, and trap them in the near field of these photonic crystal devices using basically a reflection of the tweezer light. So since then, we have actually kind of mastered these systems involving single atoms coupled to the photonic crystals. And we've also performed this kind of strong atom-photon coupling, realized atom-photon gates, realized single-photon transistors, and also learned how to efficiently outcouple this light from here into the conventional fibers. So Po will actually discuss a recent progress in the poster here. And what we would like to do now is scale up the system. So in the case of silicon vacancy centers, we could just implant them at the desired locations. So how to scale up neutral atom systems? So it's actually is a kind of a big challenge, even though there are several methods existing to entangle atoms. The key challenge now is to prepare and control individually ultra-cold neutral atoms in large numbers. Two ways exist in principle to do it. One of them is, of course, a very well-known optical lattice approach, but it is very complex, and it also requires a long experimental cycle time limited by evaporation. Another approach is the use of optical tweezers. And while it's very appealing, it has a very short cycle time, simple experimental setup. It actually has been limited by the fact that you cannot load this single atom trap deterministically. In fact, if you want to scale up to a large number of these traps, what happens is it again requires a long time to basically fill them all. So motivated by that, we actually started to explore a new approach. And the idea here is to remove entropy by observation. So basically, we start with the array of the dipole traps, and then load them stochastically, but then basically observe which traps are loaded and which are not. And then, once we have observed it, we can basically remove the empty trap and then rearrange the rest to create a regular array. And then, of course, after that, we can engineer the interactions, either dipole-dipole or tunneling, or maybe photon-mediated. So we implemented this system now in a comparatively simple experimental setup where we create this trap by a trap array by using acousto-optic deflector, which is driven by the basically by the RF field. The details of this setup will be presented by Hannes Bernian in the poster here. So let me just kind of illustrate in my last minute remaining how this idea works. So basically what we do here is we start by loading the array from the mod. And then what we do, we basically take two images. The first image, we image the unordered trapped arrays, and then basically activate a feedback loop which orders them, shifts them in this case to the left, and then we image them again. And so here is a movie showing how this procedure works. So what you see is that we can create much more ordered arrays, and in fact we can quantify these ideas by either looking at success probability versus trap size. So in one case, if we don't order, the success probability scales exponentially. In this case, the scaling is much better. Or in other ways, we can also look at time it takes to create these ordered trap arrays. And what you see is that basically under a second, we can create with basically arrays exceeding 50 atoms. We can also use this technique to keep these arrays alive. And the idea here is to keep some atoms in reservoir and basically, periodically image, repeatedly image this trap array of desired size. And if we lose the atom, we just take one atom from reservoir and bring it here. And once again, for example, we can, using this technique, can extend the trap lifetime, of this array to, considerably to basically to few seconds. So this technique, it turns out to be extremely robust and flexible. And one can, for example, create clusters of 2, clusters of 10, or one can vary geometry with each repetition. And this is actually really a very promising starting platform for scaling up neutral atom systems, both involving Rydberg interactions as well as multi-atom QT. So I think I've used up my time. So this is a summary of my talk. Thank you very much for your attention.
Thank you for fascinating talk. So there are, the time is limited. There are only one question.
Misha, what is the minimum distance between the two spots in your array?
Sorry, what the distance between?
Yeah, in the array, in the last part that you've shown, what is the minimum distance that you can put?
Yeah, so the minimum distance is actually that we were able to achieve is about 1.5 microns. And it's basically limited by the fact that this, so like the way how you generate this trap array is by just using different, by basically using different frequencies, right, creating different frequencies. And so eventually when the frequency of the kind of nearby beams starts to approach the trap frequency, that's where we see the, that this kind of lifetime of the traps goes down. And so that in the present situation, this is what determines the minimal distance. So we have some ideas how to squeeze it to maybe kind of a micron, even a little bit below, but of course eventually diffraction will be a limit.
And also, can you prepare them in the ground state?
That's right. So we have not, in these experiments, we have not actually cooled them to the ground state, but there are no reasons why it shouldn't be done. So we've done it for our single atom dipole trap. And so basically what we can create here is an array which is extremely homogeneous, so we can actually match trap frequencies and also optical transition frequencies extremely well. So it's actually, so it should work extremely well.
Okay, because the time is the limit, so let's thank Mikhail Lukin again. And now we will move to the second talk. The speaker is Stefan Ritter from Max Planck Institute for Quantum Optics. His talk is